This lesson focuses on how to calculate probabilities for the Poisson distribution when we have different intervals. So if you remember, one of the conditions for the Poisson distribution is that events must occur at a constant rate. That is, the mean average number of events in a given interval is proportional to that interval. So we have to use proportionality to adapt the parameter for different intervals. Let's see an example now. People arrive at random and independently at a post office at an average rate of 2 people every 5 minutes. Find the probability of, first part, 3 people arriving in a 10-minute period. So we are given that number of people who arrive at a post office is 2 for every 5 minutes. And in the first part, we are asked to calculate the probability that 3 people arrive in a 10-minute period. So if we define x as the random variable, number of people arriving at a post office in a 10-minute period. So x can be modeled by a Poisson variable. Now we have to calculate the parameter lambda. So we know that for 5 minutes the mean is 2. Now we have to adapt the value of lambda for 10 minutes. So here we obtain lambda 4. So x follow a Poisson distribution with parameter 4. And we have to calculate the probability of 3 people arriving. So probability x is equal to 3. Now we use a PDF for the Poisson distribution. Here it's e power minus 4, 4 power 3 over 3 factorial. And the answer is 0.19523 significant figures. This is for part A. Now for part B, the probability of more than 4 people arriving in a half-hour period. So if we define y as a random variable, number of people arriving at a post office in a half-hour period. So y follow Poisson. Again, we have to calculate the value of lambda for half-hour period. So 5 minutes it's 2. For 30 minutes, half-hour period is 30 minutes. So it's 6 times. 5 times 6 is 30. So here also 2 times 6, we obtain lambda as 12. And the probability that we must calculate is probability of more than 4 people. So we have to calculate probability y greater than 4. So it's y takes value greater than 4, which is 5, 6, 7, 8 up to infinity. So again, if you remember, when we have greater, we have to take 1 minus the remaining values of y. That is, here we have 0, 1, 2, 3 and 4. So it's y less or equal to 4. So it's 1 minus probability x is equal to 0, 1, 2, 3, and 4. We must include the 4 here. So it's 1 minus e power minus 12. When we have probability x is equal to 0, inside the bracket it becomes 1. For probability x is equal to 1, it's 12 power 1 over 1 factorial. That is 12. 12 power 2 over 2 factorial. 12 power 3 over 3 factorial. Plus 12 power 4 over 4 factorial. And the answer is 1 minus 0.076, which is equal to 0.9924, 0.992 to 3 significant figures. So this is for a half-hour period. And part C, probability of one person arriving in a 1-minute period. Now if we define, let S be the random variable. So here, sorry, it's y. S be the random variable, number of people arriving in a 1-minute period. So again, 5 minutes, it's 2. 1 minute, it's 2 over 5, which is 0.4. So S follow a Poisson variable with parameter 0.4. And we are to find the probability that one person arriving. So its probability S is equal to 1. It's e power minus 0.4, 0.4 power 1 over 1 factorial. The answer is 0.268. Let's see a second example. The number of breakages at a restaurant in a randomly chosen week can be modeled by a Poisson distribution with mean 0.8. So for 1 week, the number of breakages occur at an average rate of 0.8. So find the probability of exactly one breakage in 1 week. So part A, first part. So if we, for 1 week, the question is for 1 week. So X follow a Poisson variable, it will remain 0.8. For a chosen week, the mean is 0.8. Exactly one breakage, probability X is equal to 1. So it's e power minus 0.8, 0.8 power 1 over 1 factorial. 0.359. So here we don't have to change the interval because it is for 1 week. The second part, find the probability of exactly one breakage in a randomly chosen 3-week period. So now we have 3 weeks. For 1 week, the value of lambda, that is the mean, is 0.8. For 3 weeks, it will become 0.8 times 3, which is 2.4. So here, for the second part, we have 3-week period. So X follow a Poisson distribution with mean 2.4. And we have to calculate the probability exactly one breakage. So probability x is equal to 1, but this time the value of lambda is 2.4. 2.4 power 1 over 1 factorial. The answer is 0.218. And part B. The manager offers staff a bonus if there are no breakages in 6 consecutive weeks. What is the probability that staff receive a bonus? So if during a period of 6 consecutive weeks there are no breakages, the manager will offer the staff a bonus. So we have to calculate the probability that the staff will receive a bonus. So we have to calculate the probability that there are no breakages in 6 consecutive weeks. So for 6 weeks, the value of lambda will be 0.8 times 6, which is 4.8. The mean is 4.8. And probability no breakages, that is probability x is equal to 0. Probability x is equal to 0. So it's e power minus 4.8. So here we have 4.8 power 0 over 0 factorial. This part becomes 1. So it's just e power minus 4.8. And the answer is 0.00823.